Okay. So we were talking about a class of models that the names of Monod, Wyman, and Changeau, otherwise known as MWC models. These models are important because in a very general way, they emphasize what is called indirect regulation. The context in which one might be interested in this is when one is looking at the change of conformation, for example. So consider the conformation of some macromolecule or complex. For example, this is a sort of cartoon. Imagine that it's twisted around like this, and there is some active site where some biochemical reaction can happen, which is hidden inside the structure. So it's bent or twisted in such a way as to hide this. So you might call this an inactive state. And there is some rate at which this inactive state is unfolded out so that this particular site is exposed. So now it's active and can participate in certain biochemical reaction which it could not in this state. Okay? So you can imagine that there is some rate at which this goes from inactive to active and some rate at which it goes from active to inactive, which is controlled by the energies of these two states. Now the idea is that the rate at which you transit between this and this, or the relative population of active versus inactive, can be controlled by the binding of some ligand to this molecule. And this control is one way of controlling the balance between these two states, which is an indirect regulation, because it does not automatically speed up the rate at which this goes to this, but is an indirect effect of something binding with a certain amount of energy. So remember what we did, we drew a couple of cartoons the last time.
So why is it indirect regulation?
Because it's not directly doing anything towards exposing this, it just changes the energies of these two relative states to each other. So I'll just write that down, just to remind you. Remember that the way we drew this the last time was to sort of imagine some structure like this. And this we said is an inactive state. Then we said here is an inactive state sorry, this is inactive and it's unbound because there is nothing binding to that particular pocket that I have drawn there. This state here is active but also unbound. So similarly, I can add more states. Here is one more state, here is another state. So these states are states which are bound and inactive, and bound and active. And this little wiggly thing outside here is a signal that it is actually an active state. So this I would call inactive and bound, and this would be active and bound. So then we wrote down energies for these states. We said the energy of the inactive state was epsilon sub I. And then we said that the energy of the active state, which was unbound, was epsilon sub A. These two states here of inactive plus bound have an energy epsilon inactive plus the energy of binding in that inactive state minus the energy, so minus the chemical potential, which of adding a particle to that state, taking it out from the bath. So we imagine that these states are surrounded by some density of ligand, let that density be C, and these ligand molecules can hop from here onto that particular site. Okay? So finally here I have epsilon for the active state plus the cost of binding the ligand to this point, to the site in the active state, minus mu, the chemical potential for the ligand in solution. Okay. The other result that we used is mu equal to mu naught plus kBt times the log of C divided by a reference concentration C naught. All of these results that we derived earlier. Okay. Now that we know the energy cost for these, the weights for them is just e to the power minus beta times the energy cost. Okay, remember how we did this? We said the probability of finding the system in this state is exponential of minus beta times the energy in that state divided by a normalization. So the ratio of finding this to this is just the ratio of these, because the normalizations will cancel from the top and the bottom. Okay. So from here, from all of these energies that we write down, we can go to calculating the weights, which is just exponentials of these energies. So there are 4 energies here and therefore 4 weights. Let's describe our notation a little bit. So let me fill in something that I didn't fill in the last time, which is to say that if I have receptor plus ligand, which would go to the receptor ligand complex. So let me just write the ligand as Lig, because I want to avoid confusion with an L that I wrote down earlier. So this pseudochemical reaction describes a set of receptors interacting with a set of ligands, which can go between a complex of receptor and ligand together to this dissociation in which receptor ligand becomes receptor plus ligand separately. Okay. So this we can say happens with some rate k on, and this reverse reaction we can say happens with some rate k off. Okay. In chemical equilibrium, the number of reactions that happen in this direction must equal the number of reactions that are happening in this direction, because otherwise we would get in excess of this or this particular component. And in equilibrium, this should not change. Okay. So let us look for the current in the forward direction. So this is J for the on case. This is just the rate at which the reaction happens times the concentrations of the components involved in the reaction. So this is the conversion, the amount of product being created per unit time. Okay? It's the rate at which the reaction happens times the concentration of the different reactants. Here, this is the standard biochemical way of writing a reaction. Similarly, J off is just the off rate times the concentration on the right hand side, which is R dot ligand. J is the number, it's my representation of the current, the number of reactions happening in the forward direction, and this is the number of reactions happening in the backward direction, which just balance each other out. Okay? So in equilibrium, K on times receptor times ligand must equal K off times receptor ligand combination. Therefore, this quantity R L divided by R dot ligand must equal K off by K on, which I will call K dissociation. So this was my definition of K dissociation. I used the word K dissociation in the active and inactive state the last time, and I had some questions about why is it called a dissociation constant. And this dissociation constant is named because it's the ratio of the off and the on. The larger the off rate, the larger the dissociation constant here. And we will now try and write it, explain why this was related to the quantities that we defined the last time. So because we know this particular fraction, we can say Kd equal to the amount of receptor, the fraction of receptor that's in the state. So let me just do the Kd for the inactive state. So Kd super I. So this is the fraction of receptor in the inactive state times ligand times receptor in the inactive state dot ligand. Okay. This quantity is proportional to this Boltzmann factor over here, the inactive unbound Boltzmann factor there. So that is exponential of minus beta times epsilon I. Okay. The amount of ligand, the concentration of ligand we know, that is just C by definition. The amount of bound receptor and ligand together in the inactive state is just the exponential of this particular quantity. Okay. So that is exponential of beta times epsilon I plus epsilon B in the inactive state into epsilon of minus beta times mu. Do you agree with that? It's just sort of putting all of these factors back in. Okay. I can take epsilon minus beta mu on the top. So e to the power beta times mu is from here e to the power beta times mu naught times e to the power beta into a factor kBt into log of C divided by C naught. And these two terms cancel with each other, which means that this is e to the power beta times mu naught into C divided by C naught.
It should be e to the power minus beta C.
Correct. The minus sign. And there should be a plus. You're right about that. So e to the power beta mu gives me just e to the power beta mu naught times C divided by C naught. Okay. So now I can simplify various terms here. The first term, of course, goes from the top and the bottom, and the C also goes from the top and the bottom. C naught lands up at the top. So this is just term in C naught from here, and then a term in e to the power beta times epsilon bound in the inactive state. And I think that's all. Is that right? And there's a factor of mu naught here. Minus mu naught. Is that right? You just check that for me.
Here, KD is e to the power beta mu.
Yeah. So here beta is 1 over kBt. That's what I've used. So kBt times beta is just 1. Exponential of the log is just C divided by C naught.
How do you get this? E to the power beta mu is equal to e to the power
This one? This I just substituted from here. So e to the power beta mu is e to the power this quantity on the right hand side, which is e to the power this into e to the power this. This is the first term here. The second term is this. I can cancel these facts and get the log C by C naught. Okay? This, if you remember,
Can you just repeat how did you get KDI?
this one?
KDI.
KDI. Yeah, so this is just a general expression for the dissociation constant. So now let us imagine that I am looking at a receptor in the inactive state, which is this thing that I have drawn here. Let's just imagine that. So all of this is for the inactive state. This is some inactive object here binding to ligand and making it inactive plus ligand. So it's just essentially I'm only considering this particular state and this particular state. The inactive bound state here. Okay. For that, this is the Kd corresponding to those inactive states, which I have now written in this form, C naught e to the power Ebi minus mu naught. Similarly, Kd corresponding to the active state, so this is over here I have Kd corresponding to the inactive state. So Kd corresponding to the active state is C naught e to the power beta epsilon bound active minus mu naught. Okay. So these are the definitions that I wrote down the last time, and now this is the justification for where these came from in terms of writing down the equation, the biochemical equations. It's in the paper that I gave you, they use a combination of this notation, which is biochemical, but a lot of the statistical mechanics in terms of mu naught and so on is also there. So they justify it by saying it's just more natural to think of these things, because rather than take two separate notations completely, either purely statistical mechanics or purely thermodynamics, it's better to combine it. It makes it more easier to understand where these different terms come from. Finally, L is just the concentration of active, no ligand, divided by the concentration of inactive, again without ligand. So this is the ratio of active and inactive states which are not bound. So the term on top would have this one here, e to the power minus beta times epsilon A divided by e to the power minus beta times epsilon inactive, which is e to the power minus beta epsilon active minus epsilon inactive. This is a quantity that I defined as L the last time. So L is also called a conformational equilibrium constant. That is to say, if I didn't have a ligand at all, this would tell me what is the fraction of the molecule which is found in the active state vis-a-vis the inactive state. Okay? So, the amount of active divided by the amount of inactive, both without any bound ligand, is just given by that particular fraction here, which is e to the power minus beta times epsilon active minus epsilon inactive. Okay? It's very important because it says that the more separated these are, so suppose this is the energy for the inactive state and this is the energy for the active state. Okay? The further and further these are apart, the smaller this ratio is, because there are fewer and fewer in the active state as opposed to the inactive state. So if you think of these as two conformations of active versus inactive without the binding of the ligand, this just tells you what is the equilibrium between them, what is the fraction of one versus the other. Now usually epsilon for the active state is greater than epsilon for the inactive state. Which means that L is greater than 1. Greater than 1 or less than 1? Yeah, greater than 1. No, should be less than 1, right? If epsilon A is greater than epsilon I, this quantity becomes positive. With a minus sign there, minus beta times, it becomes less than 1. Okay? What happens is, the presence of ligand shifts the equilibrium between these states. The slightly pictorial way of saying this is the sort of case where there is no bound ligand. And here is a case where there is a bound ligand. So this might be energy of the inactive state, and this would be the energy of the active state. Now we allow the ligand to bind. This is shifted up. So now this is initially here, but now has moved to this point here. And the amount by which it has moved is the amount that is epsilon bound in the inactive state. Okay. Typically also for the situation that we will consider, this state here also moves, but it moves by a smaller amount. Okay. So this moves by an amount which is epsilon b of the active state. The closer these two are together, the larger the possibility of tuning the relative occupancies of these states, because you've allowed the ligand binding to shift the balance between them by changing their energies. Okay. So that presence of bound ligand.
These energy states are close to each other, then it would be unstable, right?
Why should it be unstable?
Because
Yes.
the difference of the energies is very less. So, little changes would cause it to go from one state to another.
That's true. Yeah.
So then that is not good, right? Because then it would become unstable.
It depends on what you want to do. No? If you want to make the occupancy of the active state larger corresponding to in comparison to the inactive state, this is a way of tuning that very sensitively. For example, suppose these were now very far away and the binding of the ligand pushes them up to the same value. Once they're at the same level, then they have identical occupancies. If they're at very well separated in energy, then there's relatively little here and most of it here. But suddenly it has jumped now from being exponentially small, say 1%, to being 50%. So depending upon how the ligand, what is the effect of ligand binding on the energies of these states, of the active and inactive states, you can thus go from a situation where you favor the active state much more in this case with ligand binding than with this case.
So if the difference between those energies will be the same, even if
If the difference between these energies is the same, then it doesn't make a difference. Because overall I can always choose the zero of my energy anywhere. So I can always choose it so that if this is the smallest energy in my system, this energy is 0. Even if I shift all the energies up, I can still say it's to be energy 0 and this will be up. So if both these energies were shifted up by the same amount, then there would be no difference at all. This argument relies on the fact that they can be shifted by differential amounts, in which case you can certainly favor this particular state over this state, which is also why it's called indirect regulation, because it's not directly doing anything, just the presence of the ligand alters the balance between the active and the inactive states. So let me just write down the results that I had the last time in that convenient notation. So we looked at P active and we wrote this as 1 plus C divided by K dissociation in the active state divided by the same thing, which is 1 plus C divided by K dA, plus I had a factor of L times 1 plus C divided by KD inactive. I think that's right. Did I get that right? Did that? Yeah. So this is the probability that the system is in its active state. And I can also count the fraction that are bound, the average value that are bound, by just picking out from these 4 states that I wrote down, those that include the bound ligand and normalizing by the right factor. So if I do that, what I will get is C divided by Kd active plus L times C divided by Kd inactive. Let me just check that. Yeah. Divided by the same normalization as here, which is 1 plus C divided by Kd active plus L times 1 plus C divided by Kd inactive. Okay. So this is just choosing 2 different things here. This is only those states which have a bound ligand and asking what is the fraction of those states in which that ligand is bound.
Both are bound.
Hmm?
Both.
Yeah, this is only the states that appear on the top are only the states that represent the bound ligand. Okay. This is the same normalization whether at the top or the bottom because it's the sum over all states. Remember we have 4 states. Earlier to write this, we only counted the active states, whether they were bound or unbound. Now we are considering only the bound states. Okay. And now you can see that there has to appear a factor of concentration on the top, because if that is 0, there is nothing bound. Whereas that doesn't need to happen here, because if this is 0, there is still a fraction that is active, and that is determined by the relative energies of the active and the inactive state.
This n bound means
N bound is the fraction of receptors with bound ligand. I'm shifting a little bit here. My language, I've said receptors because I said receptors a little earlier, but what I should say is MWC molecule because it's a little more general. An MWC molecule is a molecule with this particular, the simplest version that we've studied now is the MWC molecule with a certain set of 4 states, okay, for which we now have written these results down. It's important to note that this version of the MWC model, this version has what's called no cooperativity. So if I computed, for example, P active, that's some function that would look like this. Slowly vary between 0 and 1 as a function of the concentration on this axis. Okay. By cooperativity, what I mean is something a little more complicated. That is, suppose instead of having just one binding site for this molecule, I could have just one ligand coming and sitting there. I had a large number of binding sites. So one way of drawing that might be to draw something like this. So here is a binding site, 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 and so on. Any one of these sites, one or more of these, can be occupied by a ligand. Let us imagine that there are small n such binding sites. Then the total number of states is 2, this is either inactive or active, into 2 to the power n, which is the number of states, number of occupancy states, because each one of these n sites here can be occupied or unoccupied. Earlier, we only had one site, n was equal to 1, so I only had 4 states that we had explicitly listed and enumerated. Okay. So now I have many more states to list, I have to list all their energies out. So typically I would have to specify what is the energy of a state which is inactive plus has a certain number of bound ligands. So epsilon for the bound state inactive here, EB inactive with, let me say, R ligands bound. This is the sort of thing that I would have to specify. And then I would also have to put a factor of minus R times mu. Because if I have R ligands that are bound to these particular, to the MWC molecule, then I must take away R from the solution and account for that by paying a certain cost in terms of chemical potential. So a simple version of that model, extremely simple version of that model, is a sort of all or nothing model. So that says there are only two states. One is a state in which nothing is bound. Here for simplicity is a picture of that. And it's simply here. And here it's either there are ligands bound everywhere, and here there are no ligands bound at all. R is that fraction of n ligands that are bound. So R equal to n is all of the sites filled, but in general it can be 0, 1, 2, 3, 4 right up to n. So this is the all or nothing model, and typically this is, you could think of this as an extreme case of cooperativity. That is, suppose I had thought of in some intermediate state here in which one ligand came here and joined here, that suddenly made it favorable for all of the other ligands to come in almost immediately. So this would immediately fill here, immediately fill here, and immediately fill here. Okay. So this is a limit in which the binding of even one ligand makes it very much more favorable for all of the other ligands to bind. So it's an extreme case of a cooperativity between the different ligands in this case.
So when I ask one thing, if one ligand comes and binds it, why should others also?
So there are a couple of reasons for that. In the MWC models, you don't need to specify why that happens. But it could happen either because of a direct interaction between ligands, that is also possible. That maybe the ligands, once the ligand comes and binds to this particular substrate, it tries to deform in such a way to make it more appealing for the other ligands to also join. So there could be some element of a direct interaction between the ligands, or it could just be the ligand interacts with this MWC molecule or substrate in such a way as to allow more ligands to come. We're not specifying why. So let's just imagine that we have two states. One is this state here, which I will choose to be at energy 0. And the other is a state here, which will be at energy n times epsilon minus n times mu. Okay. Again, I have n occupied ligands coming and sitting in each one of these points on the MWC molecule. I pay an energy n times epsilon for each of them, and I pay a chemical potential n times mu for each of them. Okay? Let's imagine that both of these are, for the purpose of argument, in the active state. Earlier I made a distinction between active and inactive, but let's just say it's just one object can either be in this state or in this state. Let's for simplicity call it active. So P active is this state. No, sorry, let me just correct that. What I meant was, let this be the inactive state and this state be the active state. Okay. There are only two states. This is inactive. Let me just draw it as I do it the last time with this sort of thing poking out of it. So the probability that it's in this state is exponential of minus beta times n epsilon minus n mu divided by 1 plus e to the power minus beta n epsilon minus n mu. You know these expressions. We derived them early. You know exactly how this is a system with two energy levels. Either this can happen or this can happen. The probability that the system sits here is this quantity here, and the quantity below is just a partition function or the normalization. Okay. So this I can write again as exponential of minus beta n epsilon, and this quantity here, which is e to the power minus beta n mu, let's just simplify that and ask where it comes from. Remember that we derived e to the power beta times mu is e to the power beta times mu 0 times c divided by c naught. You remember that? Therefore, e to the power n beta mu is e to the power n beta mu 0 c divided by c naught to the power n. Okay? So now we can simplify this and get P active equal to e to the power n beta mu naught times c divided by c naught to the power n whole divided by 1 plus e to the power n beta mu naught c by c naught to the power n. So now if I define Kd equal to C naught e to the power minus beta mu naught. Sorry, just a sec. Yeah, I dropped them somewhere, so they should be there. So this is e to the power minus beta n epsilon. And this should be e to the power minus beta n epsilon. Correct, thanks for pointing that out. So this becomes Kd equal to e to the power minus beta mu naught into e to the power beta epsilon. If I define Kd like this, then you can write this very simply and elegantly in the following way. P active then becomes C divided by Kd to the power n divided by 1 plus C by Kd to the power n. Okay. So now let's just look at the effect of what happens if I plot P active as a function of C. At C equal to 0, this is 0. At C equal to 1, this quantity is 1. Okay. But now the question is, what happens in between? So I leave you to check that if I take n equal to 1, I get a curve which is very much like the curve that I drew earlier for the MWC model with just one binding site. As I hike up the n here, I get a curve that moves, becomes more sharp and sharp as I go towards larger and larger concentrations. Okay. Let me just figure out one thing from here. Yeah, that should be right. Let me just work out something on the board because I am not very sure of it. Let me set P active equal to 1/2. Let me write 1/2 equal to, and let me call C divided by KD equal to x. So 1/2 is x to the power n divided by 1 plus x to the power n. Correct? Therefore, I can write 1/2 plus x to the n divided by 2 equal x to the n, which implies that 1/2 is x to the n minus x to the n divided by 2, which is 1/2 x to the n. So 1/2 is 1/2 x to the n, which means that x to the n equal to 1, or C divided by KD equal to 1 for P active equal to 1/2, irrespective of what the n is. Okay. So that is saying that I have drawn this particular curve wrong. The curves all cross at the same point. It's just that they become steeper and steeper as I go to larger n. Okay. So the common crossing point is where P active is 1/2. This is large n and this is small n. This is called a Hill function. And usually, as I said the last time, what happens is that the simplest sort of form of WMC curve typically will not fit your data. Any data that shows the function of concentration, any level of activity or binding on this axis will typically tend to be much sharper than this. This is a way of defining that sharpness, and n, that exponent n there, is some effective exponent which is called an effective Hill coefficient. Okay. It's pretending as though there was some level of cooperativity in here to the level of 2 or 3 or 4 or 5, but it's essentially a data fitting strategy that you try to fit data to, and anything for which a Hill coefficient is different from 1 is an indicator of the fact that there is some amount of cooperativity. If Hill coefficients are larger than 1, then that is, the cooperativity is one that invites more ligands to bind once a ligand is already present. More and more like to bind. The presence is favored by the existing presence of other ligands. On the other hand, if the Hill coefficient is less than 1, that means that if one has bound, it becomes less favorable for something else to bind, for another ligand to bind. And if it's exactly equal to 1, that reduces to the old calculation that we did, in which the presence of one ligand does not either inhibit, favor or disfavor the addition of additional ligands binding to the MWC molecule.
Is this a part of MWC model or is this a different?
This is a different part, although in principle this is a different line of description in terms of some effective exponent like this. But the MWC models can also be interpreted in this way. So this is just an extreme case of the MWC model with n states, where I say I'll ignore all of the other intermediate states. I will keep all of these, maybe they're very high energy states, but I will keep only these two states, the state where everything is bound and the state where nothing is bound, in order to arrive at a description like this. But in principle, the MWC models are general enough to accommodate this and many things in between. Okay. I wanted to give you some examples.
So here the Hill coefficient is the C by KD, right?
No, the Hill coefficient is that exponent.
But exponent you mean n.
I mean n.
But
So in this case I had fixed it. I had said let us do this calculation for a certain amount of n. But here what I was pointing out was typically you will have experimental data that might look like this. it's customary to fit this experimental data with a curve that looks like this, and then say which is the choice of n that best fits this data. And could be, maybe it works for 2, maybe it works for 2.5, maybe it works, it could even need not be integer. Okay.
But n is the ligands, right?
In this way of deriving it, n is not the ligand, n is the number of binding sites.
Number of sites.
So for example, in this way of doing it, I sort of drew a picture which looked like this,
Yes.
and I said there were n of these, and they could either all be bound or none of them could be bound. So in this case, n was actually 4. And I chose a very simple example of these two different states and the energies between them.
That must be an integer.
It's not, when I fit data, it is not required to be an integer. I can just say what is the exponent here that gives me the best fit to the data. So I'm not interpreting it. I'm just saying that an exponent that is sufficiently away from 1 and is positive is indicative of the fact that there is some cooperativity involved. Later I can go back and write down a more general MWC model and see what are the different states and what are their energies that are required to give me something like this. This is only for that very simple model, and I only wanted to start with that to motivate this particular form, the Hill form. Okay. And to stress the fact that Hill coefficients, effective Hill coefficients that are larger than 1, signal some amount of cooperativity in the system. So now I wanted to describe some examples.
But sir, if I want to analyze it in the simple version, there is cooperativity or not, how will I do that? Because n will always be greater than 1.
Yeah, whether there is cooperativity or not depends upon how the energies for 1, 2, 3, 4 binding are different from the energies in which I had only one which was bound. For example, the signal of cooperativity would be, suppose I have nothing bound, so n equal to 0. Suppose I have one thing bound, n equal to 1. Suppose I have two things bound, n equal to 2. Suppose I have three things bound, n equal to 3. If these are equally spaced, then it doesn't matter how many of them have been bound. If I have 3 bound here or 4 bound, it's just n times that energy. On the other hand, suppose I have n equal to 0 here, n equal to 1 was here, but n equal to 2 was here and n equal to 3 was here. Now you can see that binding 1, this is 0, binding 1, binding 2 decreases the energy, and binding 3 decreases it even further from what it was. So this is the indication that you have cooperativity in the system because the energies depend now on how many have bound. Okay? So that's a sort of pictorial way of describing what's happening. So the example, one example that I wanted to show you was something called a ligand-gated ion channel. And either I may or someone else will discuss ion channels in some detail. But ion channels are present in the cell's membrane. So this is a bilayer membrane. And this is just a molecule that sits here. Let me just draw it like this, which allows for the passage of some other molecule, for example, either calcium ions or potassium or sodium across from one side to the other. Okay? So these are channels that allow ions to move from one side to the other, but they are gated by the presence of ligands. Okay? So whether a ligand has bound or not determines whether it switches from a conformation like this to a conformation like this. So here is a bilayer, and this is an open configuration of the ion channel, and this is a closed configuration of the ion channel. So open and closed are like our old active and inactive. You can have a situation where, so let me just draw the channel for you. So here is a closed channel, and there are several different configurations of this closed channel that I can think of. Let me just draw some here. So here this is with nothing bound. Here this is one ligand bound on one side. This is one ligand bound to another site, and this is two ligand bound here. And all of this is for the closed configuration. Similarly, in the open configuration, I could have a situation like this. Nothing bound there, something bound here but not there, something bound there but not here, and two objects bound here. So it's just a cartoon version of things that can be happening. Now you can see that this is exactly like our old MWC model, but it just has more states because it now has two binding sets. Okay, so it has 2 into 4 states, and this 4 comes from 2 squared states, which gives me a total of 8 states. Over here, the same sort of arguments that we used to think about the more general version of the MWC model also work. Each of these states have their own energies. This is the energy of the closed state, the energy of the closed state plus one ligand and the chemical potential term. This closed state plus one ligand plus another chemical potential term, plus the same chemical potential term, but a different binding energy for the ligand, because this would be in a site unrelated to this. And here I have to pay for 2 chemical potential and 2 binding energies. And the same thing would go to here.
So chemical potential doesn't depend on which ligand is bound.
No, it's the same ligand. So let's just imagine there is only one ligand that is specified by one value of the chemical potential mu. It could happen that there are multiple ligands. For example, this could be ligand number 1, this could be another ligand. So one ligand might bind here, another ligand might bind here. Then we would have different chemical potentials for those ligands. So we would have mu for 1 and mu for 2. And it just gets more complicated. Just imagine that there is one particular molecule that comes and binds and induces a certain behavior between open and closed. But again, we don't have to do this calculation to understand what it will do, because we already understand the MWC model. We know that it can change the binding of this ligand, because these are different energetic states, can change the balance between open and closed, and can allow thus the flow of these ions from outside to inside or inside to outside, as whatever may be required. Just as a consequence of this additional molecule, the ligand molecule binding, and changing the balance between these states in an indirect way. That was one example. The other example is the example drawn from bacterial chemotaxis. So remember that in the beginning we had discussed the small bacterium E. coli. We said that it was roughly about 2 microns by 1 micron. I may have also pointed out the fact that E. coli is flagellated. So it has somewhere between 3 and 6 different flagella that typically tend to be much longer than the size of the cell body itself. E. coli swims, so it moves a distance of roughly about, say, 30 micron in 1 second. And it swims in a somewhat unusual way. It swims essentially using 2 types of motion. One is called a running motion, and the other is called a tumbling motion. So if I was to look at the trajectory under a microscope, I would see something that looks like this. So this would be a run, then suddenly it would sort of do something like this, then it would move more or less in a straight direction, then it would again do something like this, then it would move like this, and then again do something like that. And maybe it would move here and then do something like that. So this trajectory is, this would be a run, this would be a tumble, this would be another run, this would be a tumble, and so on. So the motion of E. coli induced by the motion of its flagella is a combination of running and tumbling. If there is some food that is present, so let me suppose there is some chemoattractant. Then E. coli biases the ratio of runs to tumbles so that it moves towards the attractant. This behavior is called chemotaxis. Taxis means motion, so motion towards attractive chemicals. So how exactly does it do this? It does it in the following way. It does it by taking these flagella, winding them around each other to form essentially one solid-like object that rotates counterclockwise. Why it must do this in order to move? So by rotating, if it rotates as counterclockwise, then two things happen. First of all, the cell body rotates in the opposite direction and E. coli moves forward. So this is a very interesting way of moving in this very fluid environment that E. coli has, and we will discuss the reasons for why it does so in a little later when we talk about fluids and the constraints that happen when small things try and move in fluids. But here all we need to know is that when it wants to run, so this is the bacterial run, it does so by winding its flagellae into one helix, rotating that helix counterclockwise, and then moving in the forward direction. When it tumbles, what happens is that the motion of this helix goes from being counterclockwise to clockwise. That for some reason destabilizes these helical filaments. They just go back to being like this. Now they're not doing anything together on their own. Therefore, this is much more Brownian and random, this particular bit of motion, which is called a tumble. Okay?
So, why this clockwise motion gives a random?
I don't want to explain that in too much of detail. Why is it that it's just an observation, that when the ratio of the turning here, when it turns clockwise instead of counterclockwise, that destabilizes the helix. Once the helix is destabilized, all of these flagella fly apart, and then there is no motion anymore. So it's essentially largely random in these regions here. And by controlling the amount of runs versus tumble, it's possible for E. coli to move in one direction. We may describe this in a little more detail later, but I don't want to do so now. So all of this running and tumbling happens because there is a little bit of machinery here that is like a machine that rotates. So there is some rotary motor at this point here, which really acts to turn this helix along. And the energy source for this comes from the transmembrane voltage. There is a difference in electrical potential between inside and outside. That is converted into an energy that is used to rotate this. It's all very beautiful and nice, and a lot of technicalities involved in exactly how it does this. So So the way it regulates this is the following. So here is the motor, the other parts of the motor. Just to draw one part here. Over here, fixed inside the membrane. So this is, for various reasons, bacteria are somewhat more complicated than from the membrane point of view than the membranes that we have in our bodies, in our cells. So there's actually a double membrane, which I don't want to describe here in so much detail. But here is a receptor that takes in a particular ligand, which is the chemoattractant in that particular case. So this is a case where the receptor is inactive. So I can imagine two states here. One is, let me just draw this not very well, but at least at some level. I know I should have a nice picture for you, but I don't have it at the moment. So this is the motor that rotates the base of the flagellum. This is the ligand, which is either bound or unbound. So this bound state here corresponds to inactive, and the unbound state here corresponds to active, in the notation which I will use right now. As long as ligand is bound, this ligand, a molecule, a protein molecule called KY, can bind to this ligand and inhibit the motion of the rotary motor. Okay, so this line with this thing drawn through reflects the fact that it's a repressor. If there is no ligand, this KY is phosphorylated, and the phosphorylated form of KY can bind to this and lead to tumbling. And this leads to running. So provided the binding of KY is inhibited to this point, the phosphorylated KY is inhibited to this point, this thing keeps rotating and this keeps running.
Inactive means
So this is just terminology for these two states. So the inactive state here corresponds to the ligand bound state, because then this represses the activity of the motor. Okay? The active state corresponds to the ligand being released, which phosphorylates the KY that binds to this point, allows us to bind to the base of the flagellum motor in the phosphorylated state, and therefore goes between running and tumbling. Okay? So this is a very intricate system that now chemotaxis in E. coli, as well as in other organisms, is something that has now been studied very extensively. So a huge amount is known both about the nature of the motor as well as all of the complicated regulation that must happen here between the ligand binding and the corresponding effect on this binding site at the base of the motor. But this is just an example to say that again, the binding of a ligand here can trigger other effects somewhere else, and the ratio of bound to unbound that is controlled by the ligand binding exerts an indirect regulatory effect on something biochemical, which in this case is the rotation of the particular motor that we are considering.